Hi everyone, I first want to welcome you to this presentation today and thank you for coming. I'm Brian Murphy, the primary investigator on Project MICA, which stands for the Martian Ice Concentration and Analysis. I'm a planetary science major, astronomy and astrophysics major as well, in the Florida Institute of Technology Honors College. And I have a specific interest in Martian surface sciences, which is inherently why you're here today at a Martian mystery, seasonal ice in the Korolev Crater. Before we get into the cool stuff, I'd really love to talk about the contents of this talk and how we're going to be breaking it down. First, we're going to talk about the introduction, in which we dissect the hypothesis and goals and really talk about the backbone of this project, which was a paper produced by BAPS in 2017. Then we're going to talk about the methods, the resolution, the data constraints, and the manipulation of this data into actual readable science images. And lastly, we're going to talk about our results and our actual exciting Korolev Crater science images and our initial conclusions that we can draw from this and our next steps from here for Project MICA. And I'd really like to highlight this image first of all, because this image is an image of Mars and it really disproves this common misconception about Mars, that it's a dead planet. And we can see here that there is these deposits of water vapor in the atmosphere acting as clouds above the northern polar layer deposit, which is the northern ice cap. And this insinuates that the northern hemisphere is in a northern winter. And we can see down here as well that there are these large, hundreds of kilometer wide ice sheets and frost packs, which insinuates that the southern hemisphere is in a southern winter. It really shows the dynamics of this planet, along with craters here, big, large plains of dust here, volcanoes here, even as we can see right here, Olympus Mons, the highest volcano in the entire solar system at 18 kilometers in height. And really, we need to talk about the two main things that prompted this research project, which is a paper produced by Jonathan Baps in 2017, in which he outlined 3 different scenarios for cold traps. And you may be asking yourself, what's a cold trap, Brian? But a cold trap is basically just a geologic formation in which something acts like a bowl, and it allows this colder, more dense air to fall into it and keep it cold all year round. And since it's cold all year round, it can then accrete and deposit ices in it and keep those ices stable even when the temperatures above it are high above the melting point and sublimation point of those ices. And he outlined 3 different scenarios, that they would either behave as we expect them to, as normal ice sheets would, and when they get warmer, they will ablate this ice and sublimate and lose all of the ice, that they would behave unexpectedly, in which they would actually grow or some sort of unexpected change, or somewhere between there is a quasi-expected state. And he believes that they would behave expectedly and lose this ice in a process called ablation, which is the same thing as sublimation, if you know what that is, but just glacial physics terms. And he did this through an albedo analysis. However, MICA aims to prove that it would be actually an unexpected behavior or a quasi-expected behavior through cold trap understanding and atmospheric mixing of these seasonal water vapor and dust percentages in the atmosphere. And we can secondly look at this image provided by Montmesson et al., the Martian water cycle, in which it visually depicts the Martian water cycle as a function of the entire planet. And we can see here that up here, this is the northern polar residual cap and northern polar layer deposit, in which the springtime right here, it ablates and loses large amounts of mass. And this mass is converted to water vapor in the atmosphere. And this water vapor then mixes in with the dust in the atmosphere and is transported south via Hadley cell convection. And as this water vapor that's mixed in with this low thermal inertia dust, which basically means that the dust is going to react more quickly to heat, as it moves south and goes over this cold freezer called the Korolev Crater, the cold trap there, it's going to be frozen out of the atmosphere and deposit onto the surface of the cold trap itself. So we hypothesize that in this seasonal variance and seasonal transport of water vapor and dust, that cold traps do not actually ablate and lose mass, but they rather gain ice throughout spring and summer. And this is investigated through our thermal infrared analysis of Korolev Crater and our purity of ice across it. You may be asking, why are we going to talk about purity of ice? Why not just measure these, if this is new ice, if this is old ice? And this is actually going to be measured through an indirect method of the purity of ice. Because this newer ice is going to be much less pure. It's going to have these dust particles in it that is going to lower its thermal inertia to insolation, which basically means that as the sun hits it, it's going to warm up slightly faster than what the colder ice around it that is much more pure is going to be. And the main difference in this is that once the solar insolation hits it, we're going to be able to see that in our science images that hopefully there will be a change in temperature in certain regions of the ice sheet per season at these specific points. And that will be able to prove that this might actually be a depositional process and not actually be the ablation process that BAPS had originally concluded. And the overall goals of Project MICA is to look at Martian ice formations such as the polar layer deposit, as seen here, which is the northern polar layer deposit around 1,500 kilometers across. The lesser ice deposits, as seen here, which is the Korolev Crater, around 61 kilometers across and around 3 kilometers deep. The polar residual caps here, here, and here, which are seasonal caps that will wax and wane, and this is actually where the majority of our water vapor is coming from, and the dust is coming from. And the tropical and mid-latitude glaciers, which aren't actually seen in this image. And how, in addition to seasonal changes, these processes might affect the formations, such as the insolation, the amount of sunlight they're getting, the geography around them, such as the cold traps being able to keep this in equilibrium for such long periods of time, and the atmospheric mixing, how much water vapor and how much dust is actually available to be deposited onto these ice sheets. This brings us to our orbital platform that we chose. And I chose this platform to satisfy a series of constraints I imposed on the data to make sure that we are getting the best data to yield the best results for our scientific investigation. And first of all, I want to talk about the spatial resolution. And we can see here that if we got a low spatial resolution of about 4 kilometers, we wouldn't be getting very much detail or fidelity in our data. But if we have a high spatial resolution of about 1/4 of a mile or around 250 meters, we're seeing much more detail in our data. This is something that we really, really need because we want to see if there are certain regions in which the temperatures are higher, thus insinuating that it's going to be higher deposition trends and less pure ice there. And the Odyssey Orbiter has a spatial resolution of about 1/3 of a kilometer, or 320 meters per pixel in survey mode. And this is great because the Coil of Crater ice sheet, as said before, is around 61 kilometers wide, so we're going to have a great pixel density to work from. Second, we need to talk about the spectral resolutions. I said before that we're going to be thinking about the thermal infrared range, which basically sticks us between 3 microns and around 14 microns in wavelength. And the Odyssey Orbiter has this fascinating instrument on it called THEMIS, which basically is able to measure the temperatures and the brightness temperatures of the ice sheet and anything around it, especially through its band 9, which peaks around 12.37 microns. And in band 9, we chose specifically this band because it has high fidelity and high data acquisition rates and is very easy to understand and get this data from. And transmission to the atmosphere is very perfect. And lastly, we want to look at the temporal resolution. And this basically means how much time has it been since this orbiter has been there. It's actually been in orbit around Mars, collecting data for the past 19 Earth years, around 10 years of Mars coverage. So it gave us great variance to choose from for if we want to choose earlier seasons or later seasons. And ultimately, we only chose 3 different season changes for this initial verification of our hypothesis. Next, we're going to get into our results. And these images to our right are very beautiful, or at least I like to think that they're beautiful. And they didn't always start this way. They weren't always colorful. They started actually as raw black and white infrared images in which they denoted colder temperatures as black and white temperatures as warmer temperatures. And we were able to take density slicing over 100 different steps and really see how these temperatures are different from each other. And we assigned these color indexes to them to fractions of a degree Kelvin between these color indexes. And really, you may be thinking, from this point right here, where it's bright red, to this point right here, it must be on the order of 200 Kelvin, or somewhere around there between these 2 different points. But in reality, they're only around 30 Kelvin apart, not very much temperature difference here. But this fractional increase in Kelvin per shade allows us to see much more detail in the actual ice sheet in certain regions that necessarily wouldn't be that viable to look in this method before. And we also chose that our Mars year are from Mars year 33 to Mars year 35, starting in 2015 and ending just recently in February 7th of 2021. So happy Martian New Year, everybody. Congratulations, you made it. But before we talk about the actual science, we really want to understand what the solar longitude means. And this is how we measure the seasons in the Martian environment. The solar longitude of 0 is the spring equinox, 90 is the summer solstice, 180 is the autumnal equinox, 270 is the winter solstice, and we start again. I impose a strict limit around a solar longitude of about 60 to a solar longitude of about 180. So late spring to about early fall to look at these images and really pinpoint where these trends are happening. And interestingly enough, we can see that in the south and southwestern quadrants, here, 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 and here, that there are these depositional trends and that there are these higher temperatures that we wouldn't necessarily expect if this was a net ablation event as seen in this normal behavior. And this brings up our first incongruency with this normal behavior presented by BAPS in 2017. Why are only certain regions of the ice sheet warmer and not the entire unit? Because if we were seeing this net ablation event and net loss, all the heat would be coming from the atmosphere above it, since it is a cold trap. And if the heat was coming from the atmosphere above it, we would expect the entire unit to be ablating at the same rate, because the atmosphere is basically an isothermal unit. But we're not seeing this here. And this is indicative of a selective depositional process along these south and southwestern quadrants that could be due to something as simple as wind and different Coriolis effects within this large crater, as in they would deposit on one side first and lose all their water vapor before heading off to another side. And now we need to look at our next set of images to really understand the second incongruency with this argument of normal behavior, which is now the Korolev Crater ice sheet just after summer solstice, even when the temperatures are highest in the thermal unit above it and the atmosphere above it. The surface temperatures are as cold as they are in midwinter. And this is an abrupt cutoff point. And we wouldn't necessarily see this in a net ablation event. We would see that the ablation would continue to happen as long as the thermal unit above it was above the ablation temperature of the water ice. And this is just not what we're seeing. And the second incongruency is, why don't we have high surface temperatures well into late summer, and why are these temperatures so low? And this basically signifies to me that it's a cutoff transport and the mechanism of the seasonal ice cutoff in the transport of the seasonal ice mechanism, and how the deposition mechanism is directly linked to the amount of water vapor in the atmosphere. And since the water vapor is no longer there at these late season points, then there's going to be no more deposition, and it's going to reach thermal equilibrium with the ice is already present. It's going to return to its mean state of freezing temperatures, such as it is in midwinter. And we can really see after this that in our other analysis of surface temperature versus solar longitude, and this supports our second incongruency, that at a solar longitude of 110, there is a highest temperature surface average, but on the surface temperature of the Korolev Crater ice sheet, there is very little difference between this. And there is an issue in the fact that on the Korolev Crater ice sheet, it is very cold, and on the atmosphere, it is very warm, and this is just not lining up with the normal behavior. This is also seen in Mars 34 and Mars 35, in which I did the same analysis and saw that these trends were actually happening in the same places at the same times. And this is very interesting because it shows not only a single event, but something that could be happening every single seasonal change. And I would have included this, but time restrictions would not have allowed me to do this. And so our initial conclusions and steps that we can draw from this is that it is evident that the seasonal changes dominate the landscape of Korolev Crater in unexpected and quasi-expected ways, as opposed to this normal expectation rate. And where do we go from here? Where does Project Mica go from here, you may be asking? So our initial hypothesis is supported by this current qualitative analysis of the thermal infrared, but really needed to choose and prove our theory behind this, we need to do a quantitative analysis, and this will be done through the in-depth infrared spectroscopy investigation using the newer Mars Reconnaissance Orbiter and its newer instrument CRISM, which will allow us to analyze the spectra of the ice and derive the quantitative estimates of the water ice's age and its masses on Korolev Crater's ice sheet through looking at the grain size of the ice. And basically, to get into that a little bit, we need to see if there is going to be these smaller grain sizes in these warmer areas, these areas that we saw with these higher temperatures in the late spring and early summer, because smaller grain size is the equivalent of having a younger ice. Larger grain size is the equivalent of having older ice. If we can see that there is younger ice within these warmer temperature regions, slightly warmer temperature regions, then there is going to be a direct proof that this warmer temperature region has newer ice as opposed to this colder temperature region, showing that there is a net deposit of ice in these regions. And secondly, we need to do this year-round investigation in which we see if this is actually a single event happening at one point in the year, one seasonal change, or if this is happening at multiple points in the year, which is really needed to be understood. These are the references that I've used thus far, and I'd be very happy to send any of these references or documents to people if they have any more questions. And I'd now like to open up the floor to questions and see if anybody has any questions about my research or anything. And if you do not or have something later, please feel free to connect with my email below.